Hello, everyone. Welcome to today's session on dynamic programming. Today, we're going to dive into a fascinating problem called the Longest Increasing Subsequence, LIS, problem. This is a classic problem that's often asked in coding interviews and helps us understand how to use dynamic programming to solve sequence-based problems. Let's go through it step by step and learn how to solve it efficiently. Let's start with the problem statement. The longest increasing subsequence, LIS, problem asks us to find the length of the longest subsequence in an array of integers where the elements are in strictly increasing order. A subsequence is a sequence of elements that can be derived from the array by picking elements, not necessarily contiguous, while maintaining their relative order. For example, consider the array 10, 9, 2, 5, 3, 7, 101, 18. A subsequence like 2, 3, 7, 101 is increasing because each element is greater than the previous one, and its length is 4. Another increasing subsequence is 2, 5, 7, 18, which also has length 4. However, 10, 9 is not increasing because 9 is less than 10. Our goal is to find the length of the longest such subsequence. In this case, the LIS has length 4, for example, 2, 3, 7, 101, or 2, 5, 7, 18. Let's discuss possible approaches. Let's explore a few approaches to solve this problem. Brute force, recursive approach. We can try all possible subsequences by recursively deciding whether to include or exclude each element. For each element, if we include it, it must be greater than the last element in our current subsequence to maintain the increasing property. This approach has a lot of overlapping subproblems, and since we make a decision for each element, include or exclude, the time complexity is O of 2 to the power n, where n is the array length. That's exponential and too slow for large arrays. Greedy approach. Core concept. Scan the array left to right, picking the next number larger than the last chosen to build an increasing subsequence. For 3, 10, 2, 1, 20, 4, 5, 6, 7, 8. Start with 3. Pick 10, since 10 is greater than 3. Then 20, since 20 is greater than 10. No later elements are larger than 20, so the result is 3, 10, 20, length 3. Dynamic programming approach. Core concept. Break the problem into smaller parts. Define memoized array at index I as the length of the longest increasing subsequence ending at index I. For each element, check previous elements that are smaller and extend the longest subsequence found. For 3, 10, 2, 1, 20, 4, 5, 6, 7, 8, DP finds 2, 4, 5, 6, 7, 8, length 6, by systematically considering all prior elements. Dynamic programming avoids repeated work and explores all valid subsequences, ensuring the optimal solution. Why greedy fails. In 3, 10, 2, 1, 20, 4, 5, 6, 7, 8, greedy picks 3, 10, 20, length 3, but stops at 20 since no later elements are larger. It misses 2, 4, 5, 6, 7, 8, length 6, by choosing larger numbers early, ignoring smaller ones that could form a longer sequence. Why dynamic programming is better. Memoized array checks all possible ways to build subsequences ending at each position, ensuring no longer subsequence is missed. It finds the optimal length, 6, efficiently with O of n squared time, compared to brute force's O of 2 to the power n or greedy's suboptimal results. Let's build intuition for the optimal DP approach. The key insight is that the LIS problem has optimal substructure and overlapping subproblems, making it a perfect fit for understanding dynamic programming concepts. Imagine we're at index I in the array. We want to find the longest increasing subsequence that ends with the element at index I, array at I. To do this, we can look at all previous indices j, where 0 is less than or equal to j, which is less than I, and check if array at j is less than array at I. If so, we can append array at I to the LIS ending at index j. The length of the LIS ending at I would be 1 for array at I, plus the length of the LIS ending at j. Let's define memoized array at I as the length of the longest increasing subsequence that ends at index I. Then, for each index I, we compute memoized array at I by looking at all previous indices j. 0 is less than or equal to j, which is less than I if array at j is less than array at I. We can use the LIS ending at j and append array at I. So, memoized array at I equals max of memoized array at j plus 1, for all j where array at j is less than array at I. If no such j exists, memoized array at I equals 1, just array at I itself. Finally, the length of the LIS for the entire array is the maximum value in the memoized array, since the LIS can end at any index. Base case. At the first index, I equals 0. Memoized array at 0 equals 1 because the only subsequence is the element itself. We'll compute memoized array values iteratively from left to right. Let's visualize the longest increasing subsequence problem. Today, we'll walk through how to find the longest subsequence in a sequence of numbers where each number is larger than the one before it, using dynamic programming. Let's follow along with the visualizer step by step, and keep an eye on the logs for detailed calculations. Initialization. We start with a sequence of numbers, array 10, 9, 2, 5, 3, 7, 101, 18. Our goal is to find the longest increasing subsequence, or LIS, where each number in the subsequence is strictly greater than the previous one. On the screen, you see the sequence displayed in a one-dimensional array labeled sequence. Next to it, we have a dynamic programming array labeled memoized array, initialized with all values set to 1. Why 1? Because each number in the sequence can be an increasing subsequence of length 1 by itself. The logs show this initialization step. Let's move forward. Computing the memoized array. Now, we use dynamic programming to compute the LIS. For each position I in the sequence, we calculate memoized array at I, which represents the length of the longest increasing subsequence that ends at index I. The visualizer will process each index from left to right, comparing the current number with all previous numbers to find valid increasing subsequences. Index 0. We start with the first number, 10. Since there are no previous numbers to compare with, memoized array at 0 stays 1. Index 1. Moving to the second number, 9, we compare it with the first number, 10. Since 9 is not greater than 10, we can't form an increasing subsequence, so memoized array at 1 remains unchanged. Index 2. For the third number, 2, we compare it with 10 and 9. Since 2 is less than both, memoized array at 2 stays unchanged, as no increasing subsequence is possible yet. Index 3. Now at the fourth number, 5, we compare it with 10, 9, and 2. Since 5 is greater than 2, we can extend the subsequence ending at 2, whose length is memoized array at 2, which equals 1. Adding 5 to the sequence makes it of length 2. The memoized array updates to reflect memoized array at 3 to 2. Index 4. For the fifth number, 3, we compare it with all prior numbers. It's greater than 2, so we consider extending memoized array at 2, giving a candidate length of 2. Since this is greater than the current memoized array at 4, we update memoized array at 4 to 2. Index 5. At the sixth number, 7, we compare it with 10, 9, 2, 5, and 3. It's greater than 2, 5, and 3. The best candidate comes from extending memoized array at 3, which is 2, making memoized array at 5 equal to 3. Index 6. For the seventh number, 101, it's greater than all previous numbers. The best candidate is extending memoized array at 5, which is 3, so memoized array at 6 becomes 4. Index 7. Finally, for the eighth number, 18, it's greater than 2, 5, 3, and 7. The best candidate is extending memoized array at 5, giving memoized array at 7 equals 3. Step 3. Finding the maximum LIS. Now that we've computed the memoized array, we find the maximum value in it to determine the length of the longest increasing subsequence. The visualizer highlights the maximum value in the memoized array, which is 4 at index 6, corresponding to the number 101 in the sequence. This means the LIS has a length of 4. The logs confirm this result, showing the maximum and its index. That's it. The visualizer has computed the longest increasing subsequence length, which is 4. Here's the pseudocode for the O of n squared memoized array approach to solve the longest increasing subsequence problem. I've used meaningful variable names to keep the logic clear. If array is empty, LIS length is 0. Memoized array at I equals length of LIS ending at index I. Base case. Each element is an LIS of length 1. Compute LIS ending at each index. LIS length is the maximum value in memoized array. This pseudocode initializes a memoized array, computes the LIS ending at each index by looking at previous indices, and returns the maximum length found. Let's analyze the complexity of our memoized array solution. Time complexity. We use a nested loop. The outer loop runs from I equals 1 to n-1, n-1 iterations, and the inner loop runs from j equals 0 to I-1, up to I iterations. For each I, the inner loop runs I times, so the total number of iterations is 1 plus 2 plus 3 plus 2 plus n-1 equals n times n-1 divided by 2. This is O of n squared. Each operation inside the loop, comparison and max, is O of 1, so the overall time complexity is O of n squared. Space complexity. We use a one-dimensional memoized array of size n to store the LIS lengths, so the space complexity is O of n. Note on optimization. There's a more advanced solution using binary search that reduces the time complexity to O of n log n. It maintains an array of the smallest possible values for each LIS length and uses binary search to update it. We won't cover it today, but it's a great follow-up topic. That's it for the longest increasing subsequence problem. We've seen how dynamic programming helps us solve it efficiently with an O of n squared approach by breaking it into subproblems and building the solution iteratively. Thanks for learning with me today.